When you think of San Francisco, a single image instantly comes to mind. A sweeping, majestic bridge, bathed in fog. Its bright international orange towers piercing the skyline. That bridge is the Golden Gate Bridge, one of the most photographed, celebrated, and engineeringly remarkable structures in the world. But the Golden Gate Bridge is more than just a beautiful landmark. It is a suspension engineering marvel, a feat of human ingenuity and audacity that reshaped the very idea of what was possible in civil engineering. Today, we're delving deep into the blueprint of the Golden Gate Bridge, exploring its conception, its design, the engineering principles that make it stand tall, and the cultural legacy that has cemented its place in history. The vision behind the bridge. In the early 20th century, San Francisco was a city rising with extraordinary ambition. Its population was growing, its economy was flourishing, and its cultural influence was spreading across the American West. Yet for all its momentum, San Francisco remained uniquely constrained. The city sat on the tip of a rugged peninsula, separated from Marin County by a stretch of water that was as breathtaking as it was unforgiving, the strait known as the Golden Gate. This narrow opening between the Pacific Ocean and San Francisco Bay served as both a vital maritime passage and a formidable natural barrier, shaping the city's destiny in ways few fully appreciated. Before any bridge existed, ferries were the only connection. These ferry services, while essential, were far from ideal. Journeys across the strait were slow, dependent on calm weather conditions, and often dangerous. Dense fog could reduce visibility to almost nothing, and the waves could turn violent without warning. For workers, commuters, and families, the ferry crossings were a daily reminder of the city's geographical isolation. As San Francisco expanded, the limits imposed by these slow marine connections became increasingly problematic. What the city needed was a permanent, stable, and accessible link, something stronger and more reliable than any ferry could ever provide. But building that connection posed a monumental challenge. The Golden Gate Strait spans more than 1.7 miles at its widest navigable point. Beneath its surface lie some of the strongest tidal currents in North America, moving at speeds up to 7.5 knots. The winds that whip through the passage are fierce and unpredictable, capable of bending the masts of ships and sending waves crashing against the cliffs. To make matters even more daunting, the waters are deep, far deeper than the foundation levels for most bridges built at that time. Adding to the complexity, the region sits atop one of the world's most active seismic zones. The threat of earthquakes loomed over every theoretical design. For many engineers of the era, these conditions made the idea of a bridge nothing more than a fantasy. Leading experts dismissed proposals outright, arguing that no structure could withstand the violent combination of shifting tectonic plates, relentless tides, and hurricane-force winds. Even the federal government voiced skepticism, fearing a massive engineering failure. But one man refused to accept defeat: Joseph Strauss, a bold and unyielding bridge designer who had earned a reputation for innovation through his work on movable and bascule bridges. While Strauss had never built anything on the scale the Golden Gate demanded, he possessed something rare: vision paired with an unwavering belief in possibility. To him, the Golden Gate wasn't a barrier. It was an opportunity, a chance to push engineering boundaries beyond anything the world had seen. Strauss didn't simply envision a bridge that connected two shores. He imagined a structure that symbolized modern engineering itself, a testament to human ingenuity rising boldly against nature's most intimidating forces. In his mind, the bridge would be more than a crossing. It would be an icon of American ambition, a monument carved into the sky. This belief marked the beginning of one of the greatest engineering stories ever told. Designing the impossible, Strauss began with a bold yet elegant idea: to conquer the Golden Gate using a suspension bridge. At the time, suspension bridges represented the pinnacle of long-span engineering. Their defining strength lay in their simplicity: massive cables draped over towering supports, holding the roadway in place through carefully distributed tension. Unlike truss or cantilever bridges, suspension bridges required far fewer piers, making them ideal for deep or treacherous waters. And the Golden Gate Strait, with its violent currents and extraordinary depth, demanded exactly that type of solution. But even this approach was not straightforward. The Golden Gate Bridge would need to surpass every existing suspension bridge in scale. The main span had to stretch a staggering 4,200 feet longer than anything humans had ever attempted. At its completion in 1937, it would become the longest suspension span in the world, a milestone that many experts once believed impossible. The magnitude of this challenge pushed engineering into unknown territory. Recognizing the enormity of the task, Strauss did something that would change the course of the project. He assembled a team of exceptional minds to refine and perfect his initial concept. Each person brought expertise that would prove essential. Leading the engineering refinement was Leon Moisseff, one of America's foremost authorities on suspension bridge theory. Moisseff understood flexibility, an idea many engineers at the time viewed with suspicion. While traditional designs emphasized rigidity, Moisseff believed a suspension bridge needed to move with the wind, not resist it stubbornly. Under his guidance, the Golden Gate's aerodynamic profile was shaped to withstand powerful gusts without collapsing. His theories allowed the bridge to achieve its extraordinary span without compromising safety. Alongside him was Charles Ellis, a brilliant but largely overlooked mathematician whose contributions were nothing short of monumental. Ellis performed the painstaking structural calculations required to ensure the bridge could bear immense loads, traffic, wind pressure, temperature fluctuations, and the stress of earthquakes. Working day and night, often without public recognition, Ellis created the mathematical backbone of the Golden Gate. Although he did not receive proper credit during his lifetime, modern engineers recognize him as one of the project's true visionaries. Then came Irving Morrow, the architect who gave the bridge its soul. Morrow's Art Deco styling transformed the towers from mere supports into sculptural landmarks. His decision to use the striking international orange color, chosen for visibility in fog, became one of the most recognizable design choices in architectural history. Without Morrow, the Golden Gate might have been just another steel structure. With him, it became a global icon. Together, these minds, engineers, mathematicians, and artists blended precision with creativity in a way rarely seen in civil engineering. Their collaboration produced a structure that was technically daring yet visually elegant, scientifically advanced yet emotionally stirring. The Golden Gate Bridge is not only a masterpiece of engineering but a testament to what humanity can achieve when innovation, courage, and imagination come together in perfect harmony. The challenge of materials. Constructing a bridge as ambitious as the Golden Gate demanded an unprecedented quantity of materials, most notably steel. More than 80,000 tons were required to bring the structure to life, but acquiring that steel in the 1,930 seconds was no simple feat. The nation was emerging from the Great Depression. Industrial capacity was stretched thin, and transportation infrastructure was nowhere near as advanced as it is today. Every beam, girder, and plate had to be manufactured with precision, shipped by rail or barge to the construction site, and lifted into place with equipment specially designed for the project. Each step had its own challenges: delays caused by storms, supply bottlenecks, and the difficulty of maneuvering heavy components in a narrow, wind-whipped strait. The most extraordinary components were the main suspension cables, engineering marvels in their own right. Instead of pre-made cables being hauled into place, the Golden Gate's cables were constructed using a revolutionary technique called on-site wire spinning. This method required workers to pull single wires, each just a few millimeters thick, across the length of the span, anchoring them at each end. 12 of these wires formed a single strand, and when enough strands were spun together, they created a cable of unimaginable strength. Each main cable, once completed, measured 36.3 inches in diameter, containing over 27,000 individual wires. These cables were designed to carry thousands of tons of weight, holding up not just the roadway, but the constant dynamic forces of wind, temperature shifts, and seismic movement. The bridge's towers were another towering feat of engineering. Rising 746 feet above the water, they stand nearly as tall as the Washington Monument and required massive foundations. Those foundations were anchored deep into the bedrock beneath the bay, an operation that involved blasting, dredging, and heavy underwater construction in swirling currents that made visibility poor and conditions hazardous. Once the foundations were secured, steel sections were hoisted into place to build the towers piece by piece. Every bolt, plate, and crossbeam had to be positioned with exacting precision, because even minor misalignments would have jeopardized the entire structure. Even the roadway pushed the boundaries of engineering, innovation. The deck needed to satisfy two conflicting requirements: flexibility and rigidity. It had to flex under extreme conditions: thermal expansion during hot summers, contraction during cold winters, swaying under powerful winds, and movement during seismic events. Yet, it also had to remain rigid enough to support the constant weight of vehicular traffic. To achieve this balance, engineers designed a system of steel trusses beneath the roadway. These trusses distributed loads efficiently while allowing controlled, graceful movement. They gave the bridge its characteristic ability to breathe with the environment while remaining structurally sound. Every component, from the cables to the towers to the roadway, represented a blend of bold innovation and meticulous engineering. The Golden Gate Bridge wasn't just built, it was crafted, piece by piece, into a structure that could withstand nature's fury while standing as one of humanity's greatest architectural triumphs. Engineering against nature. The Golden Gate Bridge isn't just a symbol of human ambition, it is a monument to engineering in direct confrontation with nature's most unforgiving forces. From the very beginning, the bridge was designed with one central truth in mind. The Golden Gate Strait is a battlefield of natural extremes. Any structure built across it would have to endure constant punishment. Engineers weren't simply constructing a crossing, they were building a survivor. High winds were among the most formidable challenges. The strait funnels Pacific gusts with extreme ferocity, regularly exceeding 100 miles per hour. These winds can push, twist, and vibrate a structure until it fails. Recognizing this danger, engineers embraced aerodynamic principles that were ahead of their time. The bridge's deck was designed with open trusses, allowing wind to pass through rather than slam against a solid surface. The towers tapered subtly at the top, reducing drag. This was not accidental, it was precision engineering. Decades later, these design choices proved critical, allowing the Golden Gate to endure storms that would have crippled less adaptable structures. Beneath the surface, strong currents posed their own threats. The waters of the Golden Gate can reach speeds of 7.5 knots, powerful enough to sweep debris, logs, and even large vessels into the bridge's foundations. Engineers responded by sinking massive caissons, watertight chambers deep into the ocean floor, allowing workers to excavate and anchor the structure into solid bedrock. These anchors ensured that no matter how violently the currents raged, the bridge's base would remain immovable. It was a remarkable feat of underwater engineering, especially considering the technology available in the 1,930 seconds. But perhaps the greatest long-term threat was seismic activity. San Francisco lies near the San Andreas Fault, and earthquakes are a fact of life. Even though earthquake-resistant, engineering was still in its infancy. The designers understood that rigidity was the enemy of survival. The Golden Gate was built with deliberate flexibility, the ability to sway, bend, and absorb energy rather than crack under stress. This principle, unusual for its time, has allowed the bridge to withstand numerous seismic events. In many ways, the Golden Gate was a pioneer of modern earthquake engineering. Then came the persistent assault of fog and corrosion. The strait's microclimate produces thick fog that blankets the bridge for days, carrying salt particles that aggressively attack steel. Left unprotected, corrosion would have destroyed the bridge within decades. Engineers countered this with multiple layers of protective paint and a maintenance system that became legendary. Teams of painters and technicians working year-round, inspecting, scraping, and recoating the steel to preserve its integrity. The iconic international orange color wasn't just aesthetic, it was part of the protection. Each of these challenges demanded ingenuity, creativity, and resilience. The Golden Gate Bridge could not be fragile, temporary, or ordinary. It had to be a structure capable of surviving everything nature could unleash and still stand as an inspiration to everyone who crossed it. Through wind, water, earthquakes, and corrosion, the bridge has endured, proving that human engineering, when combined with courage and imagination, can triumph even over the harshest elements. Construction, triumph over adversity. Construction of the Golden Gate Bridge began in 1933, at the height of the Great Depression, a time when economic hardship gripped the nation and jobs were scarce. Yet, the bridge became more than an engineering project. It was a symbol of hope and progress. Thousands of workers flocked to the site, each contributing to a monumental endeavor that combined human courage with technical ingenuity. The work was grueling, dangerous and often performed under extreme conditions. Scaffolding swung high above the churning waters of the strait, steel beams were hoisted by cranes into gusty winds, and workers moved along precarious platforms hundreds of feet above the ocean. Every day demanded focus, bravery, and skill. Safety measures during construction were minimal by modern standards. Harnesses, helmets, and guardrails were rudimentary at best. Yet Joseph Strauss, the project's lead engineer, introduced one innovation that would save lives: a safety net suspended beneath the bridge. This net caught men who slipped or fell from the superstructure, a measure considered radical at the time. During construction, the net saved the lives of 19 workers, men who became known as members of the Halfway to Hell Club. While it couldn't prevent all accidents, the net represented a profound commitment to worker safety in an era when risk was otherwise accepted as inevitable. The technical challenges of building the bridge were staggering. Constructing the north and south anchorage points required work in deep, turbulent waters, where currents threatened to sweep away men and materials alike. Massive steel towers were assembled incrementally, lifted piece by piece into position, while engineers and crews balanced on platforms that swayed in high winds. Perhaps the most delicate task was spinning the enormous main cables in place. Workers guided thousands of individual wires across the strait, with painstaking precision, twisting and combining them into cables over 36 inches in diameter, each capable of supporting thousands of tons of weight. The process demanded perfect timing, coordination, and nerves of steel. Despite these challenges, the bridge was completed in just over 4 years, finishing in 1937 ahead of schedule and under budget. An extraordinary achievement given the scale and complexity of the project. Upon completion, the Golden Gate Bridge held the title of the longest and tallest suspension bridge in the world, a record that captured global attention. Its cost of $35 million, roughly equivalent to $700 million today, was a relatively modest investment for a structure that would become an enduring icon. The Golden Gate Bridge did more than connect San Francisco to Marin County. It transformed the skyline, redefined what was possible in engineering, and inspired generations of engineers, architects, and dreamers. From the first steel beam to the final cable, every bolt and every wire represented human ingenuity and perseverance. When it opened, the bridge was not merely a functional crossing, it was a triumph of vision over adversity, a permanent testament to what courage, skill, and determination can achieve. The aesthetic vision. While the Golden Gate Bridge is celebrated as one of the greatest feats of engineering in history, its visual impact elevates it from a functional structure to a true work of art. The bridge's striking appearance was not incidental, it was the result of careful architectural vision, primarily the contribution of Irving Morrow, the designer responsible for giving the bridge its soul. Morrow understood that a bridge spanning the Golden Gate Strait would not only serve a practical purpose, but also become a defining image for San Francisco. Every detail, from the towers to the color, was meticulously planned to ensure the structure would inspire as much as it connected. One of Morrow's most enduring decisions was the choice of color. Rather than blending into the fog or receding into the background, he selected international orange, a bold, warm hue that immediately draws the eye. The color was not purely aesthetic, it served multiple purposes. In the frequent and dense fog that blankets the strait, the bridge remains highly visible to ships navigating the treacherous currents below, improving safety. At the same time, international orange complements the natural surroundings, the deep blue-gray waters of the bay, the soft greens of the Marin Hills, and the misty skies, creating a striking yet harmonious contrast. The result is a visual statement that is simultaneously practical and breathtaking, ensuring the bridge is unforgettable from every vantage point. Equally important are the Art Deco towers, which transformed the Golden Gate from a utilitarian structure into a symbol of elegance and modernity. Rising 746 feet above the water, the towers are adorned with vertical fluting that accentuates their height and strength. Subtle curves soften the steel's imposing presence, providing rhythm and proportion that appeal to the eye as much as the mind. The towers are not mere supports for cables and roadway, they are sculptural elements, harmonizing structural necessity with aesthetic intention. Their design communicates solidity, resilience, and grace, balancing the bridge's immense scale with human sensibility. This union of function and beauty is what sets the Golden Gate Bridge apart. Every engineering decision, from aerodynamic trusses to seismic flexibility, is complemented by a careful attention to visual impact. The result is a structure that commands attention not only for its technical achievements but for its ability to inspire. It conveys strength, elegance, and possibility, serving as a reminder that human ingenuity can simultaneously solve practical problems and create lasting art. Today, more than 80 years after its completion, the Golden Gate Bridge remains not just a crossing over water, but an iconic symbol of human creativity and ambition, a testament to the idea that engineering and art are not separate disciplines, but complementary forces capable of producing something truly timeless. Engineering legacy. The Golden Gate Bridge is not just remarkable for its scale, it's revolutionary in its engineering principles. Suspension system. By transferring loads through the cables to massive anchorages, the bridge spans enormous distances without intermediate supports, a method still used in modern bridge design. Aerodynamic flexibility. Engineers learned from earlier failures in suspension bridges, most notably the collapse of the Tacoma Narrows Bridge in 1940 to allow controlled movement without structural failure. Maintenance strategy. The bridge's steel requires continuous painting to prevent corrosion. This ongoing maintenance, known as the bridge that's always being painted, is a testament to foresight in long-term engineering sustainability. The Golden Gate Bridge became a template for modern suspension bridges around the world, combining innovation, safety, and aesthetic beauty in a single blueprint. Cultural and symbolic impact. More than an engineering wonder, the Golden Gate Bridge is a cultural icon. It represents ambition, perseverance, and the human spirit's ability to conquer challenges. For visitors, crossing the bridge is both a literal and symbolic journey, a passage between history and modernity, nature and technology. It has appeared in countless films, photographs, and advertisements, becoming a symbol of San Francisco itself. Its towers have weathered earthquakes, storms, and fog, yet remain steadfast, a reminder of what careful planning, bold vision, and engineering brilliance can achieve. The bridge has also inspired generations of engineers, architects, and dreamers who see it as proof that daring projects can become reality when ingenuity meets determination. Challenges and modern upgrades. Even today, the Golden Gate Bridge faces challenges. Seismic retrofitting. Modern engineers have reinforced the towers, deck, and anchorage to withstand potential earthquakes. Traffic management. The bridge carries over 112,000 vehicles per day, necessitating careful planning and lane adjustments. Environmental considerations. Ongoing efforts protect the surrounding marine ecosystem and minimize the bridge's environmental impact. Despite these challenges, the bridge remains functional, safe, and visually stunning, a testament to the foresight of its original engineers. The blueprint of inspiration. What makes the Golden Gate Bridge truly remarkable isn't just steel and concrete, it's the blueprint of human ambition. A vision to solve a seemingly impossible problem. Boldness to challenge conventional wisdom. Precision engineering to transform ideas into reality. Aesthetic design to ensure the structure inspires, not just functions. The bridge embodies a lesson that spans generations. Engineering is not only about math and physics, but about imagination, courage, and perseverance. It teaches that obstacles, deep water, high winds, strong currents, are not limitations, but opportunities to innovate. The Golden Gate Bridge stands as a testament to the enduring power of human ingenuity. It is more than a way to cross a bay. It is a symbol of daring ambition, of the marriage between engineering precision and artistic vision. It reminds us that when we combine imagination, skill, and courage, we can create something that lasts for generations. Whether bathed in sunlight or shrouded in fog, whether viewed from the shore or driven across in a car, the Golden Gate Bridge continues to inspire awe. It is not just a bridge. It is a marvel, a blueprint, and a challenge to all of us to think bigger, reach higher, and build boldly. Because in the end, the Golden Gate Bridge isn't just a feat of engineering, it is a monument to human possibility.